will speak loud. Okay. Well, first of all, let me say hello, everyone. I know some of you, not all of them. This part of the session is a bit improvised because, in principle, Filomena was in due of this part, but she asked me to give this section. So I'm sorry that the slides appear as Triumph Summer Institute. We are not a Vancouver, obviously. So the next days I have adapted the material to the format. So I just wanted to give a brief introduction to Fresco. That, as Filomena said, this is the code that you will be using for different kind of calculations. Some of you already know quite a lot about Fresco, so this section will be maybe boring for you, but for others that are not familiar with the code, I think that it's useful if we start step by step with a very simple case, a case that is actually related to what Filomena has been explaining this morning, that is the optical model with Fresco. This is the simplest case, the simplest reaction that we can study. So let me go directly to the Fresco. So Fresco is a couple channels code, a very general, flexible code that was developed by Ian Thompson, formerly at Surrey and now at Livermore. And it has, in the opinion of those that use Fresco as we do, it has several good advantages and good things that make it very useful, probably also for you. So it's a multi-platform code you can use in Linux, Windows, Mac, and all Unix systems. Also, this is a good thing, but also this is something that makes it complicated at the beginning. You can calculate many different kind of reactions. So your first time that you go to the manual, it's easy to get confused because of that, because you have so many parameters, so many variables for so many different channels. Maybe you say, okay, I just want to do a simple optical model calculation. Where should I start? So, well, this is a good thing, and maybe also a drawback in some sense. Also, some years ago, I wrote a graphical interface for Fresco that I called X-Fresco. And the idea of this interface is just to help the people to edit the input files, and the format is compatible then with Fresco, so you can edit directly the text file, or you can edit it with a X-Fresco interface, or you can combine both things. I'll show you an example later on. Well, you can get it for free. That is also important, because in physics we don't have much money in general. So, and also there is a code, a subroutine called sFresco, that is a subroutine that allows you to make fits of different kinds of data. For example, to obtain optical model parameters from some data, but you can adjust many other things. So I think that tomorrow Filomena will give some example of sFresco, right? Or we will, at some point we will do. But today we will just run a simple case in which someone has given us an optical potential, and we just want to put it in the input and run it and understand the result. So there are two kinds of ingredients that we have to provide Fresco with. There are of course the physical ingredients of our problem. We have to identify in some way who is our projectile, our target, their masses, the angular momentum, so the physical things. Of course, the incident energy, and then in the case of the optical model, we have to give in some way some optical potential. That again, there are many ways of providing the optical potential. You can generate externally, or someone can generate a very complicated optical potential that maybe doesn't look like a Cook-Saxon, so you can read externally this potential. But in general, you usually use a parameterization in terms of this popular Cook-Saxon form. this is the case that we are going to show now. And apart from these physical ingredients, you have to specify some numerical ingredients. That is very important because sometimes we forget about this part, and you can get crazy results. And so you need to make always some checks to make sure that what you are getting is sensible. Numerically, well, the physics is here, so you also have to make sure that the physics is sensible, but also that numerically your result is sensible. So in the optical model case, we have to worry about essentially three parameters. The numerical step for the integration, that is, we have to solve a one-dimensional Schrödinger equation for each angular momentum, as Filomena has shown. Okay, so we have made a partial wave expansion of the wave function. So we have a equation for each partial wave. Okay? So Fresco will solve numerically this Schrödinger equation. So we have to provide it with a step. Typically, well, the step has to be small enough. If we use a step that is too large, Fresco will complain. So in the latest version of Fresco, will warn us about this. Also, the integration, as Filomena also said, has to be done up to a sufficiently large distance in order we can get properly the S matrix. So this means that we have to go well beyond the range of the potentials, of the short-range potentials. We can never avoid the Coulomb potential. It will be there irrespective of the distance that we integrate, but we have to make sure that we are well beyond the nuclear interactions. Okay? So this is the R match, the matching radius. At this radius, Fresco will make this matching between this numerical solution and this analytical solution. These Hankel functions, and with this matching, it will extract the S matrix, and from the S matrix, the amplitudes, and from the amplitudes, the cross-section. So this is the step that is the procedure that is followed by the code. And finally, since we have done expansion in angular momentum, in L, but more generally in J, because we can have a projectile or a target with a spin, so we have to take into account also the spins of projectile and target. We have to specify how many partial waves, how many angular momenta will be included. And also, as Filomena said, eventually the sum, when we calculate the amplitude, we have an S matrix minus 1, so eventually the S matrix will become 1 for sufficiently large angular momenta. So this is the point at which we can stop the sum. But Fresco doesn't know anything about that. So if we cut too soon, Fresco will do the calculation for us. It will give us the results, and it's our responsibility to understand the results and to make sure that they are sensible or not. Okay? So as I insist, we have to make a few checks every time we do a calculation, even if it is simple. Also, yes, this is to emphasize the fact that the maximum radius and the total angular momentum are related in some way. This is for the case, for example, of in which we have a Coulomb interaction. That is why we have the eta parameter, and this G stands for the grazing angular momentum. This corresponds to the physical situation in which the nuclei touch each other, so it's a grazing collision. So it's not, they don't pass too close, in which they will probably fuse or something. So they will just suffer a gentle collision. After that, they will separate. So there are several ways of estimating this grazing radius. This will be, in general, of the order of the sum of the radii of the projectile and target. So this is a very rough estimate, and this will give us a hint of how many partial waves has to be included. But in practice, if you are unsure about this, you can just increase the maximum radius, increase the number of partial waves, and make sure that your observables are stable with respect to the changes. Okay? This is a practical approach. Okay, so now we want to do an optical model calculation, so we have to define our optical potential that contains, in general, will contain a Coulomb part. That is, the simplest way is just to consider that we have a uniform distribution of charge, in which case we have this analytic expression. So in this case, the only parameter that Fresco needs to know, well, of course, needs to know the charges of the projectile and the target, but also the radius of this charge distribution. So in the Coulomb case, that's very simple. In the nuclear case, if we use, for example, the Guc-Saxon parameterization, that most of the cases we will use these kinds of parameterizations, then we need to specify, in general, 6 parameters. 3 for the real part, 3 for the imaginary part. These are the depth, the potential, the radius, and the diffuseness, and the same for the imaginary part. And something also very important that is a source of common mistakes is related to the convention to transform from what is called the reduced radius, small r, 0, to the physical radius. So here in the expression we have a radius, a physical radius, but what we introduce in Fresco are always this small r, this reduced radius. So Fresco will make internally a conversion of this kind. So sometimes you go to literature to pick some potential, but maybe the convention used in this particular paper is not this one. Sometimes, for example, it considers only the mass of the target. So the important thing is that the physical radius is the same. So you will have probably to adapt the reduced radius in order that you get the same physical radius as this particular reference. Okay, so what has physical meaning, I insist, is this big R, the physical. Okay. Also, it's useful that before you start running the calculations and trying to understand why it is not working and so on, you make a picture in your mind of what is the physical situation that you are trying to understand. So this is a plot, for example, of the effective nuclear plus Coulomb interaction as a function of the distance, and these are 2 possible kinetic energies. So depending on your kinetic energy, you expect different physics. So for example, as Filomena said, if we are so we have here this bump of that is results from the sum of the nuclear and Coulomb interaction. This is the Coulomb barrier. This is this maximum of the effective potential of the real part of the effective potential is known as the Coulomb barrier. So if you are well below this Coulomb barrier, you will have classically a turning point somewhere here. So this means that the projectile will not penetrate into the region of the target, will not feel the nuclear interaction, only the Coulomb interaction. So we expect to have Rutherford scattering. But if we increase the energy, then the turning point will be somewhere here, and well, or no turning point. We will start to feel the imaginary part and the absorption. So we expect to have other effects. Okay, so we will depart from the Coulomb, pure Coulomb scattering. So it's a good idea to have a picture in mind of what you should expect. And this is the input example for this case. So look at the parameters here are those here are the same parameters. So this is exactly the physical situation that we are dealing with. So the structure of the input, and now we will analyze each part, is always the same. So let me say there are 2 kinds of input formats. Where you have the old style, that is these columns, and you have to make sure that each variable goes to the exact column number 33, and then you have to count. And you go. So for some reason that I don't understand, there are people that prefer this old format, and they still use that. I prefer the new format, okay? So this is the one that we will discuss. But anyway, we respect that. We are physicists. We are supposed to be strange people, so okay. That's fine. So in the name list, this is the name list format. You have the first line is just a comment. This is to specify Fresco that we are using name list format. And then we have a set of name lists. The first one, Fresco, contains this numerical variables. As I say, we have to provide some physical ingredients, some numerical ingredients. Essentially, all the numerical ingredients are in this Fresco name list. A name list is just, a bunch of variables with some values. So we have this HCM is the step, this matching radius, the total angular momentum, the angular range to output cross sections, for example. But let me first give an outline of this structure, and then we go one by one. So you have typically this general name list. Then this partition in Fresco, a partition means just a different arrangement of projectile and target. So when we have an optical model calculation, there is a single partition. We have projectile and target, and that's all. We don't consider explicitly any other channels that may alter the nature of this projectile and target. But, for example, when we do transfer calculations, we will have at least two partitions, because the projectile will transfer or will pick some nucleons from the target, so we will have something different. So in this case, we have two different partitions, two different arrangements. Okay, this is the terminology in Fresco. And within each partition, we can have in general several states of the projectile or of the target. So this is specified through this states name list. And then later on we analyze the content. So we have to specify the properties of each state of the projectile, each state of the target that is included in our P space, according to the terminology that Filomena just introduced. And the P space is the space that we are describing explicitly. Then we will have to give the potentials. And finally, if we are going beyond this optical model, we are doing some coupled channels, DWBA, and you will be able after these weeks to do very sophisticated coupled channels calculations. Most of you will be able to do that, I'm sure. But we will start from the beginning. So we will have to provide the code with the information appropriate for the kind of couplings that we are including, inelastic excitations for some model or transfer or whatever. And these overlaps here are related to the overlaps that Jeff and Ed were discussing on the previous days. So essentially, these are the wave functions related to some bound wave functions, for example, in transfer calculations. But let's go to let's keep on the simple case. So as I say, the general variables are contained in this Fresco. It also contains the incident energy, the laboratory energy. If you go to the manual, then this name list contains many more variables. So you can just, in the name list, specify only those variables of interest for your problem. So the rest of variables are not used, or maybe some of them contain some default values that are appropriate for most of the cases. So just to avoid having here 100 variables, I just kept here the essential variables for our problem. Okay? In the manual, you will find many more variables. So these are the essential variables that we need now. I think, let me see. Okay, so for example, as I said, in the Fresco name list, we have to specify the step, the matching radius, up to which the integration will be done, the laboratory energy, the total angular momentum. This total angular momentum in general will be the result of coupling the spin of the projectile, the spin of the target, and the relative orbital angular momentum. Okay, so in general, we have these three angular momentum that have to be coupled to give the total angular momentum of the system. But in this particular example, we have alpha particles on nickel, and we have 0+, 0+, so the total angular momentum is just the orbital angular momentum. So the L, the big L introduced by Filomena. Okay? Then there are a few trace variables that control the amount of output that we want to get. Of course, if we specify many of these, the output will be huge and difficult to interpret. So we just specify those variables in which we are really interested. For example, it's always useful to have information on the S matrix, at least on the elastic S matrix. Some of these trace variables give more and more information as you increase this number. So S matrix, you go to the manual, equal to, corresponds to the elastic S matrix. You put equal 3 or 4, then it will give also inelastic S matrix, so it goes in increasing. The amount of information is related to the number here. And this is cross-section table. That is to say that we want to have also the cross-sections. Okay, next one. Next one is the partition. So we have to give a name to identify the projectile, name P, projectile name, the mass. We could use this 4, but of course, this is in atomic units, so we can use 4.0026 for the alpha particle, 1.0087 for a neutron, 1.0078 for a neutron, whatever. So you go to the tables and you can put the accurate number. I just put here because we don't need more than that. The same for the target, name of the target, nickel 58 in our example. The mass, again, could be point, blah, 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 whatever. The charge of the target. And next is a variable to specify number of excited states. In optical model calculation, by definition, we only are interested in the elastic channel, so in only one channel, ground state of the projectile, ground state of the target. This is our P space. So next, in this case, will be in optical model calculation, will be always equal to 1. And next week, we will see cases with next equal to 100, for example. So we have to specify one pair of states. I say pair because we always have to specify one state of the projectile, one state of the target. Of course, if, for example, we consider 2 states of the projectile and the target is the same, then we will repeat the same state of the target. But we always specify the states in pairs, projectile, target. Okay, so, but in this case, in optical model, we have one state. So we have only one line, one name list with the spin, intrinsic spin of the projectile, 0. This band P corresponds to the parity. EP is the excitation energy. Excitation energies are measured with respect to the ground state. So for the ground state, by definition, it will be 0. And the same for the target, JT, band T, ET. So very simple, almost everything 0 so far. And this C pot corresponds to, is an index to identify the potential that will be used for this pair of states. We can specify a different potential for each pair of states. So the code is really very flexible in this sense. So now we will go to the table of potentials to see how they are ordered. So what is this C pot equal 1? So this is the potential. In this case, we have only one potential. So the index, this C pot equal 1, refers in the potential name list, refers to the variable Kp. So you see here Kp equal 1, Kp equal 1. In general, our potential will contain several components. In this case, we have at least 2 components, one, the Coulomb part and the nuclear part. But we could include some other components. So we just use the same label, Kp equal 1, for all components, and Fresco will know that these are just components of the same potential. So you can use something very sophisticated, maybe combining volume Cook-Saxon with surface plus a spin orbit of the projectile plus a spin orbit of the target plus tensor plus blah, 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 blah. Okay? But in our case, this is not the case. So Kp is the index to identify the potential in other parts of the input. Then this AP-AT, remember that we have already specified the masses of the projectile and the target. We put 4 point whatever, 58 point whatever. So these are the physical masses that will be used to calculate the reduced mass. So these AP, AT, these masses are just used for the conversion from the reduced radii to the physical radii. So this defines what is our criterion for this conversion. In general, when you have a light projectile and heavy target, you use the criterion that the absolute, the physical radius, is the reduced radius multiplied by the heavy system to 1/3, for example. But when they are both heavy ions, then you usually use this criterion. But in this case, I just chose to make the transformation just with the mass of the target. So this simply implies that the reduced radii that will be defined later will be referred to this convention. It's just a criterion. Okay? Sometimes at the beginning it's a bit confusing, but okay. So the first line defines the masses AP, AT for the conversion, but also this type equals 0. We have each component of the potential is defined by two variables. That is the type and the shape. If we don't have shape here, this means that it is using the default shape equals 0. So type equals 0 corresponds, if you go to the manual, type equals 0 corresponds to the Coulomb potential. So the rest of the variables will correspond to this Coulomb potential. And shape equals 0 is the only possibility that we have in this case. The second line that is more interesting is the nuclear part. So type equal 1, if you go to the manual, it says type, yeah?
Why do we have to define the masses again if you define them in the partition?
Because you could have a different criterion for the conversion of the radii reduced to absolute radii that probably are not related to the physical masses. As I said, the physical masses, this has to be the actual masses, 4 and 58, because they will be used to calculate the momentum, whatever. But this will be just used for the conversion. I don't remember for what reason I chose here 0 and 58 for this criterion, but well, just a criterion. Is this what you meant? What you were asking for?
Yeah, I mean, this is the point of a lot of confusion.
Yeah.
So these masses do not get used as masses in the kinematics of the problem. These masses are only used to calculate a radius, and so they have to be in agreement with whatever your optical potential has defined for the radius. So you have to define these masses such that the radii come out right.
Yes, the important thing is this big R is what you want it to be. Yes. But this means that you can define in different ways this AP, AT, and accordingly you will have different possible values of this reduced radii. So, but the product of these two things has to be the physical radius. Yes? Is it clear for everyone? So, okay, we continue with the nuclear potential. In the nuclear part, we don't have to define again what is our criterion. This is defined already in the first line. Even if you don't have Coulomb potential, you will have a line like this just to define your criterion to convert from the reduced to the physical radii. Okay, even if you have a neutron plus something, you have a line like this to define this AP, AT. Okay, so for the nuclear part, we have also to define some reduced radii, and the criterion will be the same, this one here. So for the nuclear part, we have, as I said before, 6 parameters, P1, P2, P3, 4, 5, and 6, and the meaning is P1, P2, P3 corresponds to the parameters of the real part, in this case for the Cook-Saxon, and 4, 5, and 6 to the imaginary part. So the meaning of these parameters will depend on the type of potential that we have defined, that we are using, and the geometry of the potential that is defined through this shape. So that is something that is also maybe confusing, because if you are using, for example, a Gaussian potential, then obviously the radius will enter in a different expression. Okay? Or you can use Yukawa or whatever. Type equal 1, as I say, is a volume nuclear potential. Shape equal 0 is the Cook-Saxon. So this will be 90% of the cases will be your choice. But for example, you want to use a surface potential, or instead of a Cook-Saxon, a Gaussian potential. For a Gaussian potential, this is considered also as a volume nuclear potential, so you keep type equal 1, but the shape is no longer Cook-Saxon, something different, so it corresponds, you go to the manual, shape equal 2. So you go to the manual, this is a Gaussian potential. Okay? You will not have everything in mind. After 20 years working with Fresco, you will have 20% of the manual in mind. And after 40 years, maybe you will have 70% of the manual, but you have the manual online, so you can all the time go there and check the meaning of the variables.
We are now considering the elastic collision between the
Alpha
particle and
nickel.
C.
That's right.
So in principle, we have to use the 4 as AP. But in this case, practically, we set AP itself.
Yes. So for kinematical considerations, like to calculate the wave number and so on, the reduced mass that you have in the Schrödinger equation, you have h bar squared divided by 2 reduced mass. So this information will be taken from this partition name list. Okay, so these are the physical masses. This mass P, mass T, okay, for all the kinematics. But just as a criterion to convert from the reduced radii to absolute, to physical radii, you have also this AP-AT. That can be the same as before. If you want, you can set 4 and 58. But then you have to, the reduced radii, this P2 and P5, has to be set according to your criterion. So the important thing is that the absolute radius is what you want it to be. So imagine, for example, that the absolute radius is 4.2. You take this from somewhere, 4.2 Fermi. So I can, for example, set the criterion that AP is equal to 0 here, and AT is equal to 1, for example. And then this means that my reduced radius, in this particular case, with this choice, will be the same as the absolute radius. So I could just put here 4 point, I don't remember how much I say, and 4 point whatever. But you could also choose, as I have done here, 0 and 58. So this means that your reduced radius will not be the physical radius, 4 point whatever. You have to calculate the appropriate reduced radius such that the product of this reduced radius times this will give you this physical radius. So there are many possible ways of defining these two things, but the product of these two things have to be the physical radius. Yeah?
So you just have to pay attention where you get your interaction. So if you got your interaction from a publication, random publication that defined R as scaled by only the target mass to the 1/3 and neglecting the projectile mass in that scaling, then you have to be consistent with that. So we're insisting on this because it's a typical point for mismatches between results. It's different choices here in the definition of the radius.
So the message, when you go to a publication to pick some optical potential, you have to read carefully to know what is because typically they don't, sometimes they do, but typically people give this reduced radius, not the absolute radius. So you have to know what is the conversion that they have assumed, what is their criterion to convert. And then you just use the same criterion in Fresco, so you make sure that the absolute radius that you are putting in Fresco coincides with the definition that they are using. Okay? Some advertise. Xfresco, there is an alternative to going to the manual all the time. There is a interface that I called Xfresco that contains in graphical form the same sections that you had before. This Fresco name list, trace variables, the potential, so organized more or less in the same way. So in this case you have a comment accompanying each variable, so there is a short explanation that can be helpful to edit some input. So you can use the name list input and read it with this interface, modify the input, and then save again, and it will be saved, hopefully, in the same format used by Fresco. So this is an alternative. So this is one of the sections. This integration, this contains mainly these numerical variables. So you have here, for example, the step, the matching radius, and since you have the comments here, hopefully you don't have to go so often to the manual and so on, the total angular momentum, and the laboratory energy. This is the same for the partitions. So you have, in this case, the alpha nickel 58. So you can add here as many partitions as you want. Once you select a given partition, you will get here the list of states, name list. And you can modify all the properties and so on. So it's up to you to use directly to modify the input, the text file, or to open this. I think it's good to know, to have some minimal knowledge of how to modify the text file directly, because sometimes you have to you run the calculation in a machine, not in a local machine, it's an external machine, so you have to log in. So it's easier to open this in a terminal and to modify just a couple of variables and run some calculation without opening this. But I think it's also helpful for some of you, particularly some occasional users that you don't have all the variables in your mind, just to use this tool. Okay. So output files. You have the main output file with a lot of information. The amount of information will depend on these trace variables. There is always some minimal information, but you can get much more information depending on these variables. So this is the standard output. But in addition to this standard output, Fresco will create a number of files. Also, some of these files will be created only if you specify the appropriate trace variable. But typically you want to have at least this file, or to look at least at this file. The cross sections, the angular distribution of the cross section, differential cross section, will be printed in this 4201 for the first channel that you define. In the optical model calculation, you have only one channel, the elastic channel, so you will only get one file, 4201. If you have a couple channel calculation with two states, so you are doing inelastic excitation, for example, you will get the 201, 202. So the first one will correspond, so the same ordering that they are introduced in the input, that they are defined in the input, and so on. And this is something that I think is not in the manual, because I just knew this directly from Ian, and after converting many times from relative to absolute units. But anyway, you have a charge, projectile, and target. By default, Fresco will print the elastic cross-section divided by Rutherford, relative to the Rutherford cross-section. This is the standard choice. But sometimes you want to have also the absolute cross-section without dividing by the Rutherford cross-section. So you can get this directly by setting the maximum angle less than 0. Then also it's useful to look at the elastic S matrix. Particularly to see if you have this property that for sufficiently large angular momenta, the S matrix should go to, as a chorus now, should go to 10 to, what is, for very large angular momenta, we say that, so that you don't have nuclear interactions, you are far away from all the interactions, so the S matrix should be 1 should be 1. Okay? So you have to check, but in general, for a small angular momenta, it will be a complex number with a real imaginary part, and if we have imaginary parts, the modulus of this complex number will be smaller than 1. We will see the results now. Okay? So it's good to check that when at the maximum value, the S matrix is 1, so complex number with 1, 0. Real part 1, imaginary part 0, with some accuracy, of course. And then it's also useful to look at the FORT56 file that contains several columns. So the first column is called fusion, but I think it's better if we call it absorption. You have absorption cross-section. The second column is the reaction cross-section. I think that you have introduced this morning, or we? The reaction cross-section refers to everything that is not elastic, so everything that escapes from the elastic channel. So if we are doing optical model calculation, so our P space is just the elastic channel, so everything else will be contained in some way implicitly in our optical potential. It will come from the imaginary part of this optical potential. So we will get a cross-section, a reaction cross-section, that is related to this Q space that we are not taking into account explicitly, but is implicitly accounted for in our choice of the potential. Okay. If we have, if we are doing coupled channels, we will get an additional. An additional column, the third column that I label here as inelastic cross-section, but in general corresponds to all channels that are not elastic, but are included explicitly. So if we are doing, for example, inelastic scattering, and we include one excited state, we will get some cross-section corresponding to the population of this state. If we do transfer, then the meaning of this column, it will not be inelastic, it will be the transfer cross-section. So you see we have 3 different kind of cross-section. We have the elastic cross-section, we have this absorption cross-section, that is all the channels that we don't consider explicitly, and we have this inelastic transfer cross-section that are those channels that we do consider explicitly, but not the elastic channel. So everything apart from the elastic channel. So let me show you some results that are the same that Philomena have shown before. So in this, for this input, I think I had the energy of 10 MeV, but we can easily run the input for different energies and see if what we get is consistent with what we expect. So these are some useful kinematical variables for this problem. So change the incident energy, changes this eta parameter, this Sommerfeld parameter, the wave number, wavelength, and this 2A0 is the distance of closest approach in a head-on collision. So classically with a zero impact parameter, this is a head-on collision. In a quantum mechanical approach, this would correspond to the total orbital angular momentum equal to 0. So this is what this is describing. But this typically makes sense, is useful in classical or semi-classical approaches when we can define a turning point. So this gives us an idea of how close the projectile and the target will be in the situation in which, in the most favorable situation, that is a head-on collision. So, for example, at 5 MeV, the distance of close collision in this head-on situation is 70 Fermi. This is clearly beyond the range of the nuclear interaction. So if we plot, if you go back to the plot of the nuclear potential, it goes to a few Fermi, but certainly it doesn't go to 17 Fermi. So this means that in this situation, the projectile and the target will not feel the nuclear potential, either the real part or imaginary part. So we expect here to have a pure Rutherford scattering. So when we plot the cross-section here with respect to the Rutherford scattering, we would expect to have just one. If we plot it in absolute scale, we will get the well-known Rutherford formula. Okay? As we increase the energy, then this distance of closest approach will be smaller and smaller. So you see that, for example, at 25 MeV, it becomes 3 point something. That is clearly inside the range of this nuclear interaction. So we will have something different from the Rutherford cross-section. Also, just anticipating what we will discuss next week, it's also useful to have an idea of the wavelength of the projectile because it gives us an idea on how much, to what extent the classical picture is useful or not. So when the wavelength is small of the projectile, then we can imagine that this projectile is following a defined trajectory, so we can make approximations in terms of, instead of solving the quantum mechanical problem, maybe we can solve the motion of the projectile using some classical approximation. This is useful to simplify many reaction frameworks. And next week we will see a couple of examples of that. So this is a necessary condition for these methods to be reliable, to be accurate. The wavelength has to be small. Okay, let's go to the results. So these are the results of the output, and this afternoon you will have the opportunity to run this by yourself and to change the energy and to play with the result. But now I just show you what you should get. So these three plots correspond to the three different incident energies, 5, 10, and 25. And on the top, this corresponds to the absolute cross-section. At the bottom corresponds to the cross-section relative to the Rutherford cross-section, to the ratio between the elastic cross-section and the Rutherford cross-section. So, in the top, you have also, just for reference, I put also the prediction of the Rutherford formula that you have seen this morning. So that is the red line is just the Rutherford cross-section. So you see that at 5 MeV, the black line, so this is the result of the calculation with Fresco, is just the red line, that is the Rutherford formula. This is what we expected. We are well below the barrier, so what we get is essentially the Rutherford formula. This is just a test that the code is working as we expect. Then we increase. Yep.
I think we haven't said anything about the Coulomb at short distances, right? We regularize the Coulomb, right? Our Coulomb doesn't go as 1 over r all the way to 0, right?
What do you mean, sorry?
You've got a radius for the Coulomb, right? So you're considering homogeneous sphere.
Oh, okay. Yes,
I didn't say anything about it, so can you just...
the finite size of the... Okay, we are not using so the Rutherford formula, strictly speaking, is for a point projectile, point target. So, but we are using a finite distribution, because remember, we consider a sphere, a charged sphere with some radius. So eventually, at some point, we will expect some departure from the pure Rutherford formula, but this should appear, this is out of this plot probably, because we don't see this departure, but clearly there will be some difference between the two expressions at some point. But let's see, no, maybe here. Yeah, no, not here in this case. That probably you have to go to higher energies. So in order that you see this the picture, you need that the projectile and target get so close enough to fill this finite size of the nuclei. But in this case, the distance, for example, of Croce's approach was 17 Fermi. So the nuclei don't know anything about the size of the charge distribution. So that is probably, in this particular case, you are not sensitive to this radius. Actually, you can check this in the code by just changing this radius of the charge distribution, and you will see that you get essentially the same result. And the reason is that the nuclei don't get close enough to fill the size of the nucleus. So the Coulomb potential, the Gauss theorem will be the same for regardless of the size of the charge distribution. Okay, you understood what? Yeah.
Let's consider the spherical shape.
Yes, the finite size. Yes.
Yeah. And the results divided through
By Rutherford.
yeah, Rutherford are with that correction. Right?
Yes.
Okay.
Yes, but in this case we are not sensitive to the size. Then at, for example, at 10 MeV, the ratio of the cross section, of course, in this case is just 1. Then at 10 MeV, as we said, then we expect to have some nuclear effects, and also we might have also some effect from this finite radius of the charge distribution. So part of this difference comes from this probably from this correction of the radius, but probably most of this difference comes from the effect of the nuclear interaction, both real and imaginary. At small angles, again thinking classically, we have a very distant collision, so even if the nuclear potential is there, then the nuclei don't get close enough to feel this nuclear interaction. Okay, so remember that these values correspond to the head-on collision. So this is the situation in which the distance between them is smaller. But for any other collision, this minimal distance will be larger. So in particular, so for this region, for these small angles, we have a very distant collision, and so again we get something that resembles the Rutherford cross-section. So this will be the general case for sufficiently small angles. We expect to have always the cross-section that looks like the Rutherford cross-section, and then eventually it will depart from this. And well, yeah, if we increase further the energy, then we start to have different structures. This corresponds to this Fraunhofer regime, and this interference can be understood very nicely again in the classical picture, thinking on trajectories. So this corresponds to the interference between what it is called near side trajectories and far side trajectories. These are the trajectories that goes on one side of the target nucleus or the other side, and they are scattered to the same angle, and then they interfere. I don't know if you remember the plot that Filomena showed this morning. And this intermediate situation corresponds to what is called in heavy ion scattering the Fresnel situation, Fresnel collision. So this is a situation in which you have a maximum of the cross-section here, and then you have this depletion, this suppression of the cross-section that correspond to the trajectories that classically are absorbed by the target. So these large angles correspond to trajectories that with a small impact parameters, and many of these trajectories, when they reach the target, they are absorbed by the imaginary potential. This means that part of the flux, of the incident flux, will escape from the elastic scattering because of this imaginary potential, imaginary part of the potential. So that is why we get this, it is called a shadow region. Yep.
In the right move case, does it go to 1 for very small angles, or is it below 1?
This one, it should get 1. I think that the plot goes slightly, the scale is slightly above 1. It's 1 point something. You look carefully, it's not... yes, it is 1 actually. The scale it goes to 1 point something, the scale. So this is also a test that we can do. Okay, so this afternoon you will have the opportunity to play on your own. That is more funny than just listening to me showing with this. And also, there are things that I'd like you to consider when you run the calculation. It's a good idea to check that the calculation is sensible in numerical sense. That is, so your parameters are appropriate. So several things that you have to check. For example, is that you have include enough number of partial waves, and the way in which we can check this is by looking at the modulus of the S matrix, of the elastic S matrix. So what we have learned this morning is that the modulus of this S matrix, when we are in situations in which we don't have the nuclear interaction, should become 1. So this is what we have here. At 5 MeV, you cannot see anything because this is 1 for all values of L. At 10 MeV, you have at the beginning the modulus of the elastic S matrix is smaller than 1, as you would expect, because you have some imaginary potential. But then eventually it will go to 1. At 25 MeV, then you have this situation. Another thing that you can see from here is when you increase the energy, the number of angular momenta that are involved increases also. This is related again to this expression that this is again the grazing angle related to the grazing angular momenta. So you have the K here. So roughly the number of partial waves grows approximately at the square root of the energy. So when you increase the energy, you have to also to make sure that you increase the number of partial waves. You will have more and more partial waves involved. So this is what you have here. So in the cases that we have studied, so cutting the maximum in 20 will be enough for the 3 cases. We don't need to adjust so much because this calculation takes just a fraction of a second, so you don't need to use a value like this. And this is the reaction cross-section, but I think that we can discuss this maybe later on, because you have not said anything so far about the reaction cross-section.
But I should say, because it's part of the homework. So is this the last one, or is there?
Yes, this is the last one.
Okay.
Yeah.
So I'll get the other one up and just come to. So just very quickly, I know that everyone is hungry. I won't need this. And everyone absolutely needs to break. But just because this is going to be the last question of the homework, I want to make sure that you're not all going to ask me the same thing in the afternoon and create chaos. So we can... What I introduced before was a total elastic cross-section, and we calculated that total elastic cross-section just by integrating the angular distribution of the elastic. Now, because now we've got imaginary potentials, we're going to have flux that goes away from the elastic, and we're going to call that cross-section an absorption cross-section. So the cross-section would then be just the overlap of the absorptive part of the interaction and the wave function squared, summed over all the contributions, the partial waves weighted in the correct way by 2L plus 1. So one can calculate an absorption cross-section in this way. But also, as Antonio mentioned, we can define something called the reaction total cross-section that comes from everything that is not elastic. So how do we define a reaction cross-section? Everything that is not elastic. Now that includes absorption, and it includes other channels that we may explicitly include in our formulation.
Now, our formulation at the moment is the simplest possible formulation, where the ground state of the target, where only the ground state of the target is taken into account, where there's only the elastic channel. That's the only explicit channel we take into account, which means then that the reaction cross-section is exactly the absorption cross-section. Okay? So this is a very particular and simple case in which reaction cross-section is equivalent to absorption cross-section. You can, in any case, in any general case, calculate both the reaction and the absorption cross-section in the way it's defined. Now, the reaction cross-section, I know I discussed this earlier with Jeff. I know Jeff introduced this concept. Mod SL squared is the probability of the thing coming out, being detected. 1 minus mod S squared is the thing being absorbed, right? So, in this case, the reaction cross-section is 1 minus mod, is proportional to 1 minus mod S squared, exactly because of that. Because it's stuff that is being removed from the elastic that you're not going to detect as elastic. Now, in some cases, you're going to detect it as something else, as inelastic, or as breakup, or as other channels. And then you'd still sum it up and call it reaction. Okay, so this is an important thing because it's the last question that I have in the homework, is to determine what is the absorption cross-section and the reaction cross-section. And this is where they come from. You can look at them explicitly in the output, so that they're actually listed in the output. You can integrate your cross-sections to calculate total elastic cross-section and then work out what the absorption and the reaction need to be. Okay? So I think we should pause, enjoy lunch, and we'll see you back here. I think the standard time is around 2. Okay. So have a good break and come full of energy.